Welcome to the Explainer. Today we're going to decode the invisible logic that guides all our data across the entire globe. I mean, have you ever really thought about it? It seems impossibly complex, right? Like you're trying to navigate this ever-changing maze, but you don't have a map. But it all comes down to a set of really clever rules that just keep everything moving. So I want you to picture the internet as this absolutely massive, tangled web of computers and routers. To get from your screen to a server halfway across the world, your data needs a kind of digital GPS to find the shortest, most efficient path available in that exact moment. Okay, so let's explore the first major strategy that computers use to navigate this web. It's a decentralized approach, and it's a bit like stopping at every single corner and asking your neighbor for directions. Kind of old school, right? This is called distant vector routing, and the core idea is actually brilliantly simple. Each router, or node, only knows about its direct neighbors. It doesn't have the full picture, it just shares what it knows, and over time, a map of the network slowly, kind of organically emerges from all this collective knowledge. Okay, let's get into the nitty-gritty. So at the very start, as you can see right here, each router has a very, very limited view. Let's take router A. It knows it can get to its neighbors, B and D, and it knows the cost. You can just think of that as time or distance. But it has absolutely no idea how to get to C. As far as router A is concerned, the cost to get to C is basically infinity. And this is where the magic happens. After the first round of this digital gossip, node A talks to its neighbors. D tells A, hey, I can get to C and it only cost me 2. So A does some super simple math. Its cost to get to D plus D's cost to get to C, and bam, it updates its own table. And just like that, a path to C appears almost out of thin air. And this process just keeps repeating all across the network. Routers are constantly sharing their updated tables with their neighbors. After a few more rounds of this digital chatter, the system stabilizes, we call that converging, and then every single router knows the next best hop to get anywhere it needs to go. It's a really elegant, simple system. But what happens when a connection breaks? Yeah, this is where we find a pretty fatal flaw in this neighborly approach. This quote from the source material just perfectly captures the core issue with distance vector routing. A new, faster route gets shared almost instantly, but news of a broken link, well, that can get stuck. This is the infamous count to infinity problem. So imagine the direct path from A to its destination suddenly breaks. B doesn't know this yet. It just knows its best path was through A. But then its other neighbor, C, says, hey, don't worry, I can get there. So B happily reroutes its traffic through C. But here's the catch. C's path actually goes back through B. They end up in this crazy routing loop, passing bad information back and forth while the cost to reach that dead link just gets higher and higher, literally counting towards infinity. So, to solve this whole slow news problem, a completely different philosophy was needed. What if, instead of asking for directions piece by piece, what if every single router had a complete, up-to-the-minute map of the entire network? Well, that's exactly what link state routing does. Instead of only talking to its neighbors, every router broadcasts information about its own direct connections, its link state, to every other router on the network. This way, everyone can build their own identical, complete map of the whole shebang. It pulls this off using something called link state packets. And to make sure nobody's using an old, out-of-date map, each packet has a sequence number, higher is newer, and an age that ticks down. This ensures that old information just gets thrown out. Once a router has the full map, it runs a quick algorithm to find the best path to everywhere, all by itself. So you can really see the contrast here. Distance vector is simple and it scales pretty well because routers don't have to do a lot of work. But link state, it is way faster to react to changes because everyone gets the bad news instantly and just recalculates their own route. And that speed, well, that's absolutely vital for the modern internet. But finding the absolute best path creates a brand new problem. I mean, what happens when everyone's GPS tells them to take the exact same best road at the exact same time? You guessed it, you get a traffic jam. And this slide, wow, it illustrates perfectly what happens next. Congestion. Every router has this small waiting room. It's called a buffer to hold packets. When too many packets arrive all at once, that waiting room gets full and the buffer overflows. When that happens, packets get delayed or, even worse, they get dropped. They just vanish into the digital ether. So how does the internet manage these digital traffic jams? It doesn't just sit back and let them happen. It has this whole toolbox of smart techniques, and it basically acts like a set of traffic cops, keeping all that data flowing smoothly. The first method is sort of a gentle warning. As packets pass through a congested router, the router can flip a tiny little warning bit on them. When the destination gets these flagged packets, it sends a message back to the original sender that basically says, "Hey, you might want to ease off the gas a little, the road ahead is getting crowded." Now, if things get worse, the router can take a much more direct approach. It sends a dedicated choke packet straight back to the source. This isn't a suggestion anymore, it's a much more forceful command to immediately, right now, reduce the data rate. And in a real emergency, when the router is about to be totally overwhelmed, it performs triage. It's called load shedding. It simply starts dropping packets. But it can be smart about it, often prioritizing packets for something important, like your video call over, say, a background file download.
So the really key takeaway here is that the internet isn't static. It's not just a bunch of wires. It's a living system constantly talking to itself, using all these feedback loops to manage its own health and performance, second by second, all around the globe.
And that leaves us with a final, pretty big thought. The systems we've explored today are the invisible foundation of our digital world. They were designed decades ago based on these principles of cooperation and trust. The question is, as the internet's scale and speed just continue to explode, will this foundation hold?